to be here and presenting my work. And okay, this lecture is going to be just an introduction, the very basics for asymptotically flat spacetimes. Yes. So okay, so before going to the topic and some computations, let me first make some brief introduction of the work. So we know that a deep understanding of physical theory requires to have control on the asymptotic structure. But this is described by the asymptotic behavior of the physical fields, and this region is far away of any physical process. Okay. So, but we know that a thorough study of the global properties of the spacetime, for instance, with the yield bona fide observables in a plausible quantum description of the gravitational field. But one of the difficulties that we found in gravity, besides the nonlinearity of the theory, is that the method is playing two roles. One is a geometrical field. This means that it possesses information about the background geometry of the manifold, and also it's a physical field. And this means that it has information, asymptotic information about all the physical process inside the manifold. And this is something that I found very interesting in the original paper of Poincaré at the end of the 70s about the asymptotic structure of the spacetimes of the spacetime. So we know that the asymptotic structure has gained great relevance the last decades in the context of the logarithmic principle to the famous ADS-CFT correspondence. But however, an explicit realization about this holographic principle was found almost 12 years later. Earlier, not talking about holographic principle or nothing, but by studying the asymptotic symmetries of gravity in 3D with the negative cosmological constant. And this was found by Brown and Henneaux in the 80s, 86. And they found that the asymptotic symmetries, or the canonical realization, I will say that what is canonical realization, but is finding the generators of the asymptotic symmetries of this theory gives us the conformal symmetry in 2D. But we have two questions here. What is asymptotic symmetries? Well, it's a symmetry that preserves the asymptotic behavior of the fields. And what is the conformal symmetry? Well, conformal symmetry is the information that preserves the angles of two lines. In 2D, this symmetry is infinite dimensional. This means that you have an infinite amount of generators for this symmetry. And the algebra is given by two copies of the Minkowski algebra, as surely now. So this here is the famous Henneaux and Troessaert that for the theory for gravity, 3 dimensions given by this expression. Well, L is the ADS radius, and G is the gravitational. Is the Newton constant. So with the lower combination of these L's.
Sorry, Oscar, can I interrupt you? Like, I can't hear you very well. It's a little bit like muffled, the sound of your microphone.
Maybe it's my iPad. Can you hear me now?
Oh, yes.
Yes, because I have a, yes. Sorry.
Okay, thank you.
I have a fan here.
Yes. Okay, no, yes, that's great. Thank you so much.
Okay, so with the lowest modes, this means minus 0 plus minus 1, we have the Lorentz generators. And with the higher modes, we can construct the conformal group and also this infinite dimensional tower of generators. Okay. But what's happening in higher dimensions? Well, unlike the ADS case, because ADS case in 4 dimensions, this was shown by Henneaux and Troessaert in the 80s. The asymptotic structure in that case is just the ADS algebra, which is SO3 3,2. It's finite dimensional, but GR, in absence of cosmological constant, is much better from this point of view, and it has shown to be extremely rich. And this is because of the work of Bondi-van der Burg-Metzner-Sachs. They found that the asymptotic symmetries and then infinity are described by an infinite dimensional extension of the Poincaré group, where the Lorentz group, or the usual Poincaré group, is extended by an arbitrary function of the angular coordinates. And this is what we call, and the people call nowadays, VMS group, but we know that there is an ORB here for van der Burg, which is hidden. Okay. So very recently, I want to talk about this at the end of the talk, once we have, and we know what is the VMS group and how it's obtained, about the relation with Weinberg's theorem, the memory effect, which is very famous now, infrared triangle, which connects very different aspects in the study of gravity and quantum field theories. And also it has gained a lot of relevance also in the context of the information loss paradox in black holes. I will come back, I hope to come back to this question if I have time. Okay. Also, possible holographic description of asymptotically flat spacetimes. In this case, we have two. Until now, we have two so far. One is the celestial holography proposal, which is a proposal coming from the scattering, gravitational scattering problem in quantum gravity. And the other one is the Carolian, it's the conformal Carolian field theory in 3D. Celestial holography is about a celestial CFT in 2D, but the conformal Carolian field theory is about a VMS invariant field theory in 3D. And this connection is possible thanks to the work by Duval, Gibbons, and Horvath, who realized that VMS is isomorphic to the conformal Carol group. I will show, and I will talk about this also once we have the VMS group. Okay, so in this lecture 1, I will give an introduction, very basic introduction to the VMS group. I will show you how to construct the diagram, the Penrose diagram that Ignacio showed us in his lecture. In the case of Minkowski's, just in the case of Minkowski spacetime. Then we will define what is an asymptotically flat spacetime at null infinity. We will define what is the Bondi coordinates or Bondi gauge. And also we will see what is the structure of the VMS group. The next 2 lectures are dedicated to study the asymptotic symmetries of electromagnetism and also asymptotically flat spacetimes, but from the Hamiltonian perspective, what is the title of my lectures. Okay, so, but we will go to that tomorrow and Wednesday. Okay, so let's start with the Minkowski line element in Cartesian coordinates, which is very known. And we know that we can write it in spherical coordinates through in this way. Here it's important to have in mind the range of the coordinates, because this is going to be very important in order to draw the Penrose diagram. Okay, so the time goes from -infinity to infinity. The radius is always positive, and theta and phi are the typical angles of the sphere. Okay, so now this is the way that the people construct the diagram is going to retard and advance null times, whose expression is given by these equations here. But now U and B they run freely from -infinity to +infinity. Okay, this is standard. And in this case, the line element takes this form, and one can check. You can check it very easily, maybe in the computer, or if you are smarter, you can just computing that for U constant and B constant, you obtain radial null geodesics. In one case, with U constant, you obtain an outgoing null geodesic, radial outgoing null geodesic, and in the case where v is constant, the advance time is constant, you obtain the radial ingoing null geodesic. Okay, so now we will compactify the null coordinates, and for this we make this coordinate transformation, where you can see here that we can factorize by a conformal factor, and we have this method here. Okay, so but what's happening in the extreme, in the extremal cases, which correspond to u and b, the absolute value of u and b equal to infinity, which is capital U and capital B equal to pi halves. And we can see that in this case, the conformal factor diverges. So we are putting all the divergences when we go to infinity in this conformal factor. That I will call it psi. Maybe I will need it in the future. I'm pretty sure that yes, I will need this name. So please remember psi, which is equal to cos u to cos capital U times cos capital B. Okay. So now we are going to define what is inside of the square brackets, something that we call the physical metric. And this physical metric is really important. So we obtain this multiplying the line element by the inverse of the conformal factor to the square. And some properties about this physical metric. This metric does not satisfy the Einstein equations, obviously, because it's conformally related to the first one, that was Minkowski spacetime. Also, this metric does not faithfully represent physical distances also because of the conformal factor. But the nice thing about this metric is that it preserves the causal structure. So we can study now the causal structure of infinity in the case of Minkowski spacetime. So we can reach infinity, as I said, and we can cover the regions where infinity is located. Okay. So now we go to time-like and space-like coordinates, and we will draw the conformal structure of the flat space-time. Okay. So for that, we define these two coordinates here, t and r. Okay, and I have here the answer. I don't know if you can see it here, but I will try to show you a couple of things. So we had that u was time minus r and b was t plus r. This means that b is greater than u, and also means that capital B is greater or equal than u. So this means that if, for instance, b is equal to pi halves, this means that u it's going between minus pi halves and pi halves. But if b is equal to minus pi halves, this means necessarily that u is equal to minus pi halves. This immediately tells us that that the range of the time-like coordinates is going between minus pi and pi. And also that the radius, the capital radius, capital R, is going from 0 to pi. Okay. Okay. So now this is represented in this triangle here, where in the vertical axis we can see that t is going from minus pi to pi, and r is going to from 0 to pi. So we have to analyze what is each point. This can be easily done by using the change of coordinates that I already wrote you. But because of the time, I will just tell you the answer. This is what we call the time-like past time-like infinity. And if you replace the values t equal to minus pi, yes, and r equal to 0, you will obtain that u and v are given by this expression here, and you can realize that this point corresponds to a lot of points with an arbitrary radius, and when the time goes to minus infinity. So this is the point where all the is the starting point of all the time-like geodesics that will end in this other point. I will talk about this point, and this point is what we call future time-like infinity. Okay, and this is the ending point of all the time-like geodesics. Okay, another interesting point is the one where t is equal to 0, but r is equal to pi. This point corresponds to a point in this graphic, but it's not a point. It's really infinite points, as I will tell you in a moment. And this is what we call spatial infinity. Okay, and this is where r goes to plus infinity and the time is arbitrary. And also we have these famous two lines. The first one is this one, what is called square minus, and represents past null infinity. And we can see here that this is really a line equation with a positive slope. Okay, and we can see that here this point, all this point corresponds to capital U equals to minus pi halves and be arbitrary. And this means that U goes to minus infinity and little b can be an arbitrary value. So this is what we call a past null infinity. Okay. And then we have the other line, which is where each point is in a sphere. And this is a line equation with a negative slope. Okay. And this is what we call, sorry, future null infinity. Okay, I forgot to say something about spatial infinity, that this is the ending point for all the spatial geodesics, space-like geodesics. So all space-like geodesics will end at this point. Okay, all the null geodesics will arrive to null infinity, and also they are all coming from past null infinity. Okay, I hope this is clear. So, okay, I have a mess here, but if you erase all what I said, you obtain the nice Penrose diagram of Minkowski spacetime. Also, something that I said is that here spatial infinity, unfortunately, is a point, but we know that it's not a point. Why? Because at this point, it arrives all the space-like geodesics. So all the times that exist, all the hypersurfaces at constant time will arrive to this point. So the slope of the curves arriving to this point are different times, but we can resolve this point by changing the coordinates to go into a better foliation in such a way that we can describe spatial infinity. One example of this is, for instance, a hyperbolic foliation of the spatial of the flat spacetime, and for that it's useful to use, for instance, what we know as the Ashtekar-Hansen foliation, which is a foliation of the spacetime with topology R times ds3. So the ending points S-1 and S1 equal to 1 describe what we call the future of past null infinity. as null infinity. And here we have the past of future null infinity. And the utility is very useful to use the Ashler-Hansen, this hyperbolic foliation, to describe spatial infinity when you want to solve the equations. For instance, for the scalar field on a Minkowski background, given some initial data, the scalar field, you can solve the equation for the gauge potential from Maxwell equation, or even for the Pauli's field, for the linearized case of spin 2, the Pauli field. So, and this is because the equations, in this case, they are decoupled in this foliation, this hyperbolic foliation. So you can find different patches in order to describe different sectors, different regions of the flat space.
Oscar,
but
you have a
yes,
question from Ignacio.
Yes.
Oh, hey, Oscar. One
Yes.
question. I didn't really understand like how you got the new coordinate system. Is it possible like to draw one of those foliations, those Cauchy foliations that you had in the new picture on the right?
Yes.
Do you know what I mean?
Sorry. Yes. For instance, you can track a region like this, and the foliation is, I will erase this one, and the foliation is going to be something like that. When you are approaching to spatial infinity. So you can also draw a foliation which is adapted to time-like infinity, for instance, future like time infinity, and the foliation is going to be something like this. Let me draw it, something like that.
Oh, and those look like straight lines on the diagram on the right?
Yes, exactly.
Okay, okay, cool.
Yes,
Okay.
exactly that.
Thank you.
Okay, so I hope that I was enoughly clear, but because of the time we have to follow. So we have now, I think that we have the Penrose diagram. We know how to construct the Penrose diagram to read which is the conformal structure of flat spacetime. And now some comments about this diagram. So we have the topology of null infinity, which is the union of square plus and square minus, has the topology of R times S2. But the induced metric on these surfaces is singular. This is because even or in a future null infinity or past null infinity, we'll have a zero with the coordinate that we are describing the evolution through the surface. So we have something like this. Okay. So, and also we have a surface and a function that is manifestly zero when we evaluate it on null infinity. And this is a conformal factor. So the gradient of the conformal factor will describe the evolution through this null surface. And we have this induced metric and the correct parametrizations that I won't write here, but okay, this is, it's not difficult to find under some change of coordinates. So we have that the correct parameterization scribe, under the correct parameterization scribe, we can find that the geometry of null infinity is described by a conformal Carroll structure. But what is a conformal Carroll structure? Is something that is defined by this normal vector here and this singular metric, where we have that the normal vector, the vector is has inner product equal to 0 with the singular induced metric on the scribe. But that is a conformal structure or Carroll structure. Well, this is something that started more or less at the same time of EMS, but they didn't realize of this connection. But the Carroll group was discovered in the 65 first by Levi-Leblanc, and also by Sengupta in 66. 1966, and it describes the vanishing the limit where the speed of light the speed of light vanishes, and in this case it means that the light comes close up. Okay. Also, what is different about the algebra, the Carroll group or the Carroll algebra with respect to Poincaré, is that the boost, if we take two Lorentz boosts, we'll have a spatial rotation. But in this case, these are commutative. And also the energy acts like a central charge on the algebra. So it's very different to Poincaré. And the geometry described, or the geometry associated to the Carroll group, what we call Carroll geometry nowadays, was first introduced by Henneaux at the end of the 70s. But he was studying a totally different context. He was studying the zero signature gravity limit, or also the strong coupling limit of GR by Isham and Tetegon, some papers that were published in, I think, 77 and 78. They were worried about all other problems, but Henneaux realized that really the algebra of diffeomorphisms, in this case, in the case of zero signature gravity, is really related to the Carroll group. And Henneaux described, he found what is the dynamics and the action principle associated to this geometry with this structure, with this metric, singular metric, and this normal vector. And he found that he found an action principle, or something that we call nowadays the electric Carroll limit of Einstein gravity. In a very nice paper by Henneaux and Salgado Rebolledo, they found that it's possible, and Salgado Rebolledo, to construct more Carroll limits from Einstein gravity. So they found something that we call electric Carroll limit, and another thing, an equivalent description, an equivalent limit called magnetic limit of Einstein gravity. But the one that Henneaux wrote, the action principle that he wrote, was the electric Carroll limit of Einstein gravity. Okay. So one thing is that what is the Poincaré group is something that I mentioned before, but something that I have to define yet. And are the symmetries of the Minkowski spacetime? The symmetries are the vectors that are satisfying this condition here. These are given by 4 translations, 3 spatial rotations, and 3 Lorentz boosts. So we have 10 generators. Okay. So the thing is that near null infinity, one can show very nicely that these Killing vectors become conformal Killing vectors of the Carroll structure. This means that for the induced metric and the vector and the vector field, they are satisfying this equation. So the asymptotic value, again, the asymptotic value of the Minkowski Killing vectors become conformal Killing vectors of the Carroll structure. But one could wonder what is the more general symmetry preserving the Carroll structure, so satisfying this equation. So if we make a change of coordinates and we write these Minkowski Killing vectors, the asymptotic form of the Killing vectors in coordinates u, r, theta, and phi, we'll find that this is the vector that is preserving the Carroll structure, which corresponds to the lowest values of the spherical harmonics. But one can check, and this is a very nice computation, that really an arbitrary spherical harmonics is going to preserve the Carroll structure. So we'll have that an arbitrary function alpha is the one that is preserving the Carroll structure, and this is something that we call supertranslation. So the most general symmetry preserving the Carroll structure is the BMS. Okay, and now yes, we will go to what is the DMS group. But for that, we have to define what is an asymptotical flat spacetime at null infinity. Okay. So following the initial work by Bondi and collaborators, it was really two papers. One was Bondi-van der Burg-Metzner, other one was Sachs. They showed what are the coordinates that are going to parameterize the asymptotically flat spacetimes. And for that, they defined a null hypersurface given by this equation here. What is really related in the flat and asymptotically to the retarded time. And it has a normal vector, which is given by the gradient of the hypersurface. But we know that all tangent vectors lambda mu to this hypersurface must be perpendicular to k mu. But we said that this is a null hypersurface. And this means that k mu, the norm of the vector must be equal to 0. And from this equation here, we can easily arrive to this conclusion. And the reason is this one. I'll compute it very fast. We have this one. So we can see here that this is only can be mu. And this means that the temporal time component of the inverse of the metric must be equal to 0. We can also see that k mu is null. Since k mu is null, we can find that the integrals of this vector describe outbound radial outbound null geodesics. And this is something very easy to show because we can take, for instance, this is the equation of the geodesic, right? And this, and this is equal to mu lambda. So, mu lambda k mu mu k lambda. But we knew that k lambda was a total derivative. So we can change here the order of the indices. And okay, and we obtain that this is really a total derivative k mu. So because this is null, the integrals of these vectors describe geodesics, null geodesics, and these are growing through the parametrization that the foliation that Bondi and collaborators define. Another feature of these coordinates and another requirement is that the angular coordinates are not changing along the path through the tangent that is tangent to the constant cone with u constant, and this is given by this expression here, and this implies that the time angular component of the inverse metric must be equal to 0. Again, one has to use the definition of k mu in terms of the metric, for instance, and one can easily see that the mixed time angular component is 0. So we have that these components of the inverse metric are 0, and if we take the inverse of that, we will find these conditions: that the radial component of the metric must be 0, and also the mixed radial angular part must be 0. So we can write now a line element for our space that is given by this expression here. But there is one thing, that still have too many variables. Why? Because we have one here, here we have 3, and here we have 2. So we have 7, if my maths are right. Yes, we have 7, which is too much because we know that the metric must have 6 independent variables. And in order to solve that, Bondi and collaborators impose some condition on the radial coordinate, defining something that's called the luminosity distance. What is saying that the area covered by the base manifold is really the area of the sphere. So this is a very strong condition. And if we parameterize the metric of the base manifold in this form, we will find that the determinant of this metric H must be the determinant of the two sphere. Okay, so we have 7 independent variables plus minus 1 condition. We have the 6 independent variables that we wanted. So this is the Bondi line element. But also we need one condition more, and is that the spacetime must be asymptotically Minkowski. And this means that in retarded coordinates, this must takes the form of the Minkowski metric. So all these conditions is what we call Bondi coordinates or Bondi gauge. Okay. So what about the fall-off of the Bondi gauge? Well, this is the fall-off. It's something that you can find in the original papers, and it's supposed to be describing most of the solutions of the theory. Okay. So we will describe now the content of the fall-off. Here we have the metric of the two sphere, which is fixed at the boundary. This means that we cannot vary, or we cannot vary this function, this metric. And the other ones we can all vary. Little m is what we call mass aspect of Bondi mass, and something that is we can check very easily is that if, for instance, if we take the Schwarzschild metric in the usual coordinates, okay, and we use this chart of coordinates, okay, and we define the retarded time with this chart of coordinates, but we obtain the metric in the Hamiltonian future sign coordinates. Okay, and we can read from here that beta 0, and also that this little m that I show you here is really describing the mass of the Schwarzschild solution. But this for an arbitrary metric could depend on time and angles in principle. So now we'll call to the time derivative of this function that is appearing here, that is called the shear. The time derivative is what we call the Bondi-News tensor. A good explanation for this name is maybe taking the temporal component of the Einstein equation, and one can realize that we have a balance law for the loss for the loss of mass, and we can see that if this NAB is equal to 0, then the mass is constant in time. We are not losing energy at null infinity. Obviously, if we have matter here, we'll have more terms here related to the matter, but we are not considering now the contributions from the stress energy tensor. So the determinant condition that I already told you says that this tensor CAB must be traceless, and also we need an initial data in order to solve the Einstein equations, and with this initial data we can solve all the Einstein equations and find an arbitrary solution from there, but in this form. But now let us explore what is an asymptotic symmetry and finding the asymptotic symmetries for this space-time. So an asymptotic symmetry is going to be an diffeomorphism that preserves the asymptotic behavior of the gravitational field. Well, this transformation is generated by an asymptotic Killing vector, chi mu, such that infinitesimally, in this way, must be compatible with its fall-off. And this, what is compatible, that it takes the same form after applying the transformation, the same fall-off. Okay, So once you use this condition that I already told you, we'll find the asymptotic killing vector fields and also the transformation laws of the free data. What is the leading orders of the fields, of the follow of the fields that I already told you. So the spoiler of this thing is that we'll find that the group of diffeos that is preserving this this line element is really the BMS group, or what nowadays we call the conformal Carroll group E3. So here we have to compute a bit. I will go fast. I will try to go fast, but the key equation to be solved is this equation here, where we have to introduce the fall-off of the fields. But what we can solve very easily are the time components of the generator of the asymptotic symmetry, the time component and also the angular component. And for that, we use the gauge condition that is GRR is equal to 0. This means that the variation of GRR must be equal to 0, which is a Lie derivative. But we know that GRR is equal to 0, then this term is 0, and the only thing that we have is this one. But we also knew that this was equal to 0. So the only component that is surviving here is what is lambda equal to mu. And this means that the time component of the asymptotic diffeomorphism must be radial independent. So it's an arbitrary function in principle of time and angles. Then we have to solve the other condition that is equal to 0, and then from the Lie derivative, we find that this first term is equal to 0, and we have to expand these terms using the Bondi conditions. And finally, we obtain this equation here. Then, in order to find this vector here, we have to take the inverse of this metric, which it can be done, but I just wanted to show you that it's possible to just introduce the fall-off of the fields and solving this equation order by order. So one sensible answer would be that this angular component is constant at infinity. One could, for instance, have something that's linear in the radial coordinate, but we would find that this constant, this function in front of the radial coordinate must be 0. So if we solve order by order, we will find that the leading order must be an arbitrary function of u and xa, and also this sub-leading order is the angular derivative with respect to the function f, which was the time component of the asymptotic killing vector. So we find the time component of the asymptotic killing vector and the angular component. But we still have to find which is the asymptotic or the fall-off of the radial component of the killing vector of the generator of the asymptotic symmetries. And we'll find that the radial component can be completely determined in terms of f and fa, which were the leading terms in the fall-off of the remaining coordinates. And we will find that this fa is really a conformal killing vector of the sphere. It takes whose equation is given by this expression. Okay, so for doing that, we go to the purely angular part, and this is equal to something like that. And we said that this is fixed. So the variation of that part is 0. So this means that the variation of the angular part of the metric must be of order R. Okay. So from there we obtain that the angular part of the metric must be of order R. One sensible answer would be taking a linear function of the radius, And we can solve to order R squared and to order R. To order R squared, this must be 0. And this implies this equation here. We can take the trace of this equation, and we will find that lambda must be equal to minus 1/2 times the divergence of the conformity vector Fa. So if we replace again lambda here, we will obtain the equation for the conformity vector Fa. And also from the order R of the asymptotic Killing equation given by this expression, we obtain the transformation law for the shear for CAB, which is related to the news. But from the determinant condition, we knew that the trace of CAB must be equal to 0, and this means that if we take the trace of the variation, this must be equal to 0. And from there, it's really easy to see that mu must be given by this expression. And this is because if we contract this equation here by GAB, this is going to be 0, this is 0, and this is 0. And we obtain only two, so this is 4, only 2 terms times the derivative with respect to, sorry. So the derivative is going to be 1/2 the Laplacian of f, leading to this equation here. So we completely determine the asymptotic behavior of the radial component of the vector field, and we obtain this result. Now, what about the U dependence? Well, for that, we have to go to the remaining coordinates, the remaining components of the metric, and we can easily find that from this condition, this condition means that the Killing vector, the conformal Killing vector must be 0, the time derivative of the conformal Killing vector must be 0. This means that it's not depending on time, and also f, which is a function associated to the time component of the asymptotic Killing vector, must take this form in terms of u, right? And the second condition tells us that this equation must be satisfied, this condition here. But using the value of f that we already computed and the value of lambda, which was equal to the minus 1/2 of the divergence of the conformal Killing vector, we obtained that the time derivative of g0, this means that this is a constant, so it can be absorbed in this arbitrary function of the angles alpha. So finally, we obtain the generators of VMS transformations, which are parameterized by alpha and Fa. If we take the modified Lie bracket, and this is because really in these subleading terms, we have dependence on the metric. So we have to introduce this Lie bracket, this modified Lie bracket for these vector fields. And we obtain these transformation laws for the VMS, for the parameters. Here, okay. And we see that a general indeed, the general solution of the conformal Killing equation is infinite dimensional, but it's easy to show, and this you can show, this you can find in any conformal field theory book, the first 2 pages, is that only the globally well-defined conformal transformations are 6, and this is the homogeneous Lorentz group parameterized by this function Fa. Okay, and also we have an infinite dimensional extension of translations, which is parameterized with this alpha. Okay, so this is going to be the VMS group. It's going to be the semi-direct product of the Lorentz group with supertranslations parameterized by alpha. So some comments to finish.
Do you have a question, Oscar?
Yes. Please.
Thank you very much. Oscar, can I ask you a question regarding the Lie bracket? Because you are using the Lie bracket of Bondi-van der Troessaert. However, I never understood why you enhance the bracket in that way. Yes, with that variation. There is a reason to enhance the bracket.
Yes, exactly.
In that
Exactly,
form?
because you are you have a dependence on the metric in the sublimit terms of the asymptotic Killing vectors. So you have to transform. What this variation means is that we are taking the variation of the metrics of the metric dependence of T2 along T1.
Yes, I know that, but there is my question is, there is maybe another way to enhance the algebra, or there is a more deep reason because in order to consider metric dependent fields, or I don't know if you understand my question. It is, there is a more deep reason why you will enhance the Lie bracket in that form. I can enhance it, for example, in another way in order to consider metric dependent fields, for example.
I'm not sure about that, but this is something that's even before Troessaert. I think this is appearing already in the original paper by Brown and Henneaux. They have to use this modified bracket.
Okay.
And I think that there is another paper by Brown and Henneaux. Maybe there is more detail about that, because you have two papers. One is the famous one with the central charge, and there is another one with all these kind of details. But you can see here that this bracket is antisymmetric in 1 and 2, and is closing under the. I don't know if there is another definition, but it's sensible. To be honest.
Thank you.
Okay.
Okay, Oscar, you just have like a minute.
Okay, so very fast. We obtained that the conformal Carroll structure is preserved by the VMS group, which is very nice. We can have two classes of superrotations. One are the local conformal transformation, that is considering all the solutions of the conformal Killing equation. And also we have the smooth vector fields on the sphere, which were proposed by Campiglia and Lava, where you can generalize the symmetric of the sphere to an arbitrary function. These were shown to be related to the sublimits of Grafton theorem of Cachaso and Strominger. Also, the construction of surface charges and generators can be realized, can be performed through covariant methods. This was done in these papers by Barnish and Troessaert. And also the presence of radiation leads to some problems, because we cannot find an integral form for the charges, so we have to modify the boson bracket with a term in such a way that we can close the algebra. Also, this very nice result, maybe you have some seconds to describe it, that it's a Harvard school that they found that the VMS invariant, the asymmetrics of the gravitational problem is VMS invariant. And this is connected with the Weinberg theorem, Gravity theorem. And this is because they're imposing some antipoda matching conditions, which is very sensible, very nice. It's something that is satisfied by the linear Bihar potentials. That is describing just the point that I told you, which is the spatial infinity. From there, Strominger showed that we can find an infinite of conservation laws, which corresponds to the preservation of the energy and angular momentum and each angle of S2. But all this construction was performed on by assuming a certain class of spacetimes called Christodoulou-Kleiner spacetimes. One can show that the shear takes this form for this class of spacetimes, and if one takes this supertranslation variation of the shear, in the case where there is no radiation, where the radiation already passed away, one finds that C is shifted by alpha in this way. And this is the origin, and that they found, Strominger and Chioel in this very nice paper, that this is the origin of the memory effect. However, further studies by Henneaux and Troessaert, they show that these matching conditions, the ones that I wrote here, are really a consequence of having a well-defined symplectic structure. What I will explain in the next lectures. What do I mean with well-defined symplectic structure? But is really a finite action principle and finite symplectic, finite and canonical generators. And also we found in this very recent paper that with Mark and Cedric, that is not necessary to take as a condition to find these matching conditions to impose that the shear takes exclusively this form, and also can have another part that we call magnetic part, which is really related to parity violating terms when one describe a tensor on the two sphere. Okay, so that's all. Thank you.
Okay, thank you, Oscar. So let's give Oscar a round of applause. Are there any questions for Oscar? Pedro, please. No? Ah, sorry. Any questions? No, okay. Well, there will be a discussion later today, so you can ask questions there. And then, so let's give another round of applause to Oscar. Thanks. And then we'll take a 10-minute break. And then we'll have Lucia. Pedro, do you have a question or not? You raise your hand again.
I'm sorry, it keeps popping up and I don't know what I'm doing. Sorry.
Okay. So we'll connect again. And we'll restart the discussion in 10 minutes. If within this time there's any questions for either Oscar or Ignacio, please feel free to ask them.